Okay, thank you. Well, first of all, thank you for the invitation to be involved in the forum. And I know it's late, and I will try to be quicker and simple today. And one of the beauty to be the last, that you can see the question in the chat and see what people is, taking from the previous speaker. So I will use also that during my presentation. And my presentation today is mainly about contract, really, because Sarah was more in the mixed system. So it's contract depositional system, paradigm for the water sedimentary environment. So this is the outline for the talk, an introduction, review some diagnostic criteria based on seismic, sedimentary facies, logging, and something about sandy versus muddy contourites. Then I will go quickly into the implication and then go into the future consideration. So my talk is mainly focused for those that are less familiar with the topic and for the non-believer. That means people that know the topic, but they are not completely convinced about the importance of these deposits in the water and in the exploration in the water. So going to the introduction, Contourites started in the 60s with the pioneer like SM in 1966, and other authors that recognized ripples and bedford in the very deep water and started to relate the bedford with oceanic circulation, and also using a monochannel high resolution signal line, and started to identify morphologies that they were by that time completely new for the community. But since then, during the 80s and also during the 90s, the main focus on contract was to try to classify this deposit into the deep water environments and also to try to go into the cementological characteristic of these deposits. And then later, from the 90s to, I would say, 2010, researchers started to integrate morphological, cementological, and seismic facies in the characterization of these deposits. And since then, 2010 to today, I would say, there are a boom, a completely explosion of groups and research projects about the topic. And all the results from this new research were in new research lines like ignofacies or microfacies or the chemical characteristic of contourites, and also try to do experiment on numerical modeling, monitoring the mother ocean in order to understand more the processes and to understand more the deposits. So I think we are now in that phase, but including also today new processing techniques, machine learning methods, and AI to characterize this deposit. So we are now there, but it's an authentic evolution in the topic so far. So contourites. It's interesting because my experience during the last 10 years, I would say that in academia, but mainly in industry, that still people assume that the deep water environment is very quiet. I have seen some question in the chat that is linking to this comment. So maybe it's because the formal definition from contourites, because the formal definition from contourites in the 60s was that contourites are those sediments due to the influence of thermaline currents. And here you can see the modern day global oceanic circulation, the thermaline system. That is very weak in general. The average is less than 5 centimeters per second. When you go to the western side of the oceans, of the marine basin, it's higher, it could be 10 to 20 centimeters per second. But again, it's very weak. So we all assume that the deep water is weak in terms of energy, and these kind of deposits are therefore fine-grained sediments. And it's not possible to have coarser, gravel, or sandier contourites because the influence of the oceanic circulation. But there is something interesting that don't really consider, or we don't really consider much of the time, that we normally speak about water masses and current, we don't really differentiate these two types, because water masses is a body of water with physical properties. It's defined by physical properties. Normally, we simplify in surface, intermediate, and deep, but it's more complex than that, because in some ocean we have today, for example, 6 or 7 water masses. For example, here in the Southern Ocean, you can see from this work from this also different water masses, surface, intermediate, and deep in this part of the ocean. And all these water masses are important in shaping the morphology of the seafloor. And then we have currents. But currents is not because of the physical properties, because the movement of the water. Because different processes, could be the wind, could be Coriolis, could be cabling, and other, potential processes. So basically, I want to say that the two concepts are different. One is function of the physical or chemical properties, and the second is a function of the speed. In the short term, it's important. When we are talking in geological term, in the long term, the two concepts are, associated in a more closer way. But what about the modern day definition, or the definition that we are using at the present? So we use the concept of contourites for those deposits that have been deposited or substantially reworked by the persistent action of bottom currents. We don't use benthic currents, we use bottom currents. And this is a definition from Doresto and Revesco in different publications. So here you can see bottom currents in the Northwest Pacific Ocean in around 700 meters. By the way, the faces are very sandy. Why we consider bottom current? Because the definition for bottom current that we use is that they are semi-permanent water masses flows with the capacity of load transport for depositing sediment on the seafloor. So it's not anymore thermaline currents or thermaline system in the definition. And the reason is because there are other processes, as Elda and Sarah and others today explained before. So there are a number of secondary oceanographic processes like internal waves, internal tides, eddies, etc., enhanced or modifying the background, the geostrophic current, the thermaline system. And most of these secondary processes are very energetic. And some of them, the velocity associated with this secondary process could be more than 100 centimeters per second, much more higher compared to the thermaline circulation. And with this velocity, because the influence of these secondary processes, we could have coarser sands or even gravels in the deep water because the influence of these processes. Therefore, my main message for this introduction is that the deep marine basins don't exactly represent the weak, low energy sediment-starved environment that traditionally is assumed. And here in this figure, you can see the distribution of the bottom currents globally. And in yellow and red, you can see the area with higher velocity. You can see that maybe along the lower slope, continental rise, and because the interaction of this thermaline system and these secondary processes with the irregularities, the velocities could be very, very high, more than 100 centimeters per second in many areas. That is why the influence of oceanic circulation, and that is why we could have in the deep water sedimentary system pure gravitational system, for example, fluidity system. We could have when the currents and oceanographic processes are dominant pure water system, because the interaction of the two, as Sarah explained very well before, mixed systems, and also in areas with less influence, hemipelagic or pelagic deposits. But the reality is that all the systems interact laterally and vertically all the time. So what are the criteria of the main ones? So normally we use drift for the larger bodies of sediment affected by water masses and bottom current. This is a drift that was, this is a drift from the South China Sea, and the term was defined in the 60s for Hessen and Johnson in this fantastic book, The Face of the Deep. And there is different type of drift. 9 type of drift are considered in the literature. Probably there are more, that they are less known, but we all assume that at least there are 9 type of drifts. So what does mean? That in a contract system, we could have a great variety of drift, not only Mount drift, but also we can see, because the influence of bottom current, other features. As a more erosional, they are mixed. And this is important because we can see, as I said, the positional feature, for example, a drift, erosional feature, for example, channel or mohawk, because they are different concepts. We can see erosional surface, or we can see what we call mixed feature. It's not a mixed system, it's mixed feature because the processes are changing on time, and sometimes some features are more depositional and then changing for erosional. And that is why it mixed. But the reality is that all of the features, laterally and vertically, are together, forming what we call a contourite depositional system. That is a concept similar to, for example, turbidite depositional system. But it doesn't mean that all the deposits on the drift or in the erosional element necessarily are contouritic. The reality is that on this drift, we could have turbidite, we could have a worker turbidite, we have mass transport deposits, fine-grained contourites, quartz-grained contourites, and others, as we see in pure gravitational systems. So there is a variety of sediment, and something that we hypothesize, because it's a working hypothesis, that these contourite depositional systems are linking to one particular water mass. For example, here you have water mass 1, water mass 2, and there is an interface or a transitional zone between the 2 water masses. So the drift, the depositional element, or you allow me to say the main deposcenter of sediment, is with the energy is minimum. So not necessarily when you have a stronger current, you have more sedimentation. In fact, it's the opposite. The main deposition is where the currents are weaker. When you move laterally to the position of the currents, of the core of the current, is where you have more erosion. And in those settings in which you should expect to have coarser sediment. For example, in this example, I included in yellow the potential location of, for sandier deposits, and then in green, more fine-grained sediments. So the thing is that all these quartz sediments are here because of gravity, but then laterally affected by the water masses and also by the secondary processes. For example, in these interfaces are the key areas for the influence of the internal wave that was explained before, the internal tides, or the processes. So these areas are really depths in the ocean which there is maximum energy and which the processes have more capacity of transporting and eroding sediments, or water sediment. What about the criteria? Here you have this nice example from Newfoundland, and there is some basic criteria. For example, drifts in general are parallel to the margin, parallel to the irregularities. Internally, there is a upslope or upper relief migration of the deposits, but there are other. Normally, there is a key or basal surface that usually is an erosional surface. There is internal discontinuities that normally represent also internal erosional surfaces. There is non-stratigraphic conformity between the top surface of the drift with internal layer, and there is a hierarchy of high to low deposits when you are from the core position laterally in the drift, but also up current to dock current. So the variability is in 2 dimensions, not only in 1. Normally, in this kind of system, there is different steps in the evolution of the system, starting for the onset, that normally is characterized by tabular drift or shitty drift, and then evolving to the growing phase that normally is among the drift. It's a general assumption because it's not that simple, but let's say that by now. And how to identify this, or how to develop a seismic analysis of these deposits? What are the criteria? Normally, we study this system at different scales. In a large scale, try to identify the larger feature that we call the third order feature, and then we go into the subunits to the medium scale to see the stacking pattern of the deposits, and then we go into more detail in the third order level to identify the seismic phases of bed fault within the subunits. So there is a hierarchy in the way we do the seismic analysis to characterize these deposits. Normally, the drift and the contour system are huge because they are associated to water masses. For example, today the Antarctic bottom water mass is following all the oceans, the southern hemisphere and in the northern hemisphere. And associated to this water mass, we have laterally, time to time, huge drift. So these drifts are in a basin scale. They are not local. They are even larger than the gravitational system. So what is happening to identify this drift is you are working in regional 2D seismic line. It's even easier than if you are working in 3D seismic data. So you cannot really see the dimension of the feature. So if you are going to identify this drift, I would suggest to see first the regional 2D seismic line and then go into the detail of the feature with the 3D seismic data. Here you have in this sketch from Adam Kirby the different steps, onset and growing. Some people consider also a maintained stage at the end. And for example, the drift is a third order. The channels or moats or terraces are also third order because they are very large. And as a second order feature, you could have erosional surface or small terraces, scar, furrows, scour gullies, and so on. Or sediment wave or other bedfall or mastrapo deposits, channel overland deposits, turbidite, etc. So they are smaller in scale compared to the freshwater problem. In terms of reflectivity, we know relatively well where the high amplitude anomalies are associated to the different drifts, to the 9 types of drifts I mentioned before. So we know that mainly the high amplitude anomalies in seismic 2D or especially in 3D are within the channel associated to the terraces or in front of the gateways or straits. An example of this secondary feature are, as I say, sediment wave. Here you have a nice example from Hanford, from Tennessee. And you can see perhaps here the morphology of sediment wave. Here another example of sediment wave in plan view from the Cretaceous in Namibia, where you can see a submarine canyon from there to here, crossing the margin. And then laterally you see you have these wavy phases that they are sediment wave. And the interesting thing of this example is this: there is sandy deposits or sandier deposits with high amplitude anomalies between the wave crests, initially linking to the sediment supply through the canyons and then reworked by bottom currents laterally. Another example, there are these sandy ribbon from Norway, or a secondary feature of these amazing sandy dunes and furrows, as well from the Norwegian margin that you can see here on the right. So these secondary features are very common, and with the 3D is a fantastic tool to identify this smaller feature, very indicative of the influence of these bottom currents. In terms of sedimentary phases, there is a great variety of phases, depending on the velocity associated to the bottom currents. Here you can see in red the threshold velocities from hemipelagic to muddy contourites, or from muddy contourites to sandy contourites, and then with more than 80 centimeters per second, the possibility to have erosion in the seafloor. This is mainly for siliciclastic components, and we have to consider when we have more bioclast components, the velocity are weaker. For example, to have calcareous or sandy or sandy deposit composed by bioclast, the velocities could be not 20 centimeters per second, could be only 15 centimeters per second, because the hydrodynamic behavior of the class is, different compared to the density compared to the siliciclastic particles. In terms of the sedimentary phases, we all assume a model for contourites that is mainly working in fine-grained contourites. And this is that we call the bigradational sequence that initially was defined by Gontier et al. In 1984 in the Wool of Cadiz, it's out of Portugal, and then refined and changed a bit by Joachim and Jean-Claude Fourier in 2008. So this is the typical sequence of phases for contourites, where sediment fine-grained contourites are evolving to sandier in the central part, and then quartzing outward, and then fine outward in the top, from sandier to muddier again in the upper part. That is why the degradation trend in the segment. In logging, for example, these sequences could be identified using gamma ray, with a lower gamma ray in the central part and higher in the lower and the top part. And density, velocity, and receptivity logs could be also useful to identify this asymmetric variation for these contourite deposits. But this second of phases is very common, and it's mainly on drift. It's not in the channel, it's not in the front of the channels, it's not in the terraces, it's mainly in where you have the main deposit on the drift. And when you move distally, you can still see the variational sequences, but thinner. The variational sequences, the average is around a meter or half a meter, but we have seen a variational sequence with more than 10 meters in some areas, or even thinner. And when you move distally, the thickness of this variational sequence is very, very thin. When you go proximal in the system, you started to see asymmetric sequences, and the top part is eroded away, especially on terraces. Another thing is the deposits, the sanded deposits in the erosional elements, mainly within the channel or in the mixed element, mainly on the terrace. These are the areas where you can identify in environment dominated by bottom current quartz sediment. You can see gravel, you can see quartz sand or fine-grained sands in this environment. The thing is that so far there is not a sedimentary phases model for the sandy deposits. Have been studied by different authors, but still we have not a model for these quartz deposits. And then here in these proximal areas, we could have a worker turbidite, we have proper turbidites, and distally perhaps pelagic and pelagic, and that's the normal. Within a system, within a contour system, we have laterally and vertically the association of all these phases. That is why it's not simple to identify this deposit on the field. And that is why it's not simple to identify this deposit when you have a well, when you are working with logging data. Here you have an example of sandy deposits in around 1,000 meters in Southwest Pacific. This is a video from a recent paper from Shannon Frey, sorry, and you can see this deposit affected by bottom currents, the scour of the current interacting with these blocks and irregularity. There are a number of examples where people identify sedimentary facies. And there is some analog, good analog in the field to see pure contourite facies. For example, Cyprus or Morocco or California could be more reworked, or different areas, Angola, for example, where some different also propose facies for this fine grain and coarser grain contours. I selected two to show you very quickly. One is from Cyprus that we have been working for years here. And here you have an example from the field, from an outcrop. This is middle Miocene in age of these variational sequences. So let me use this name that I know they are not so well considered at the moment. Cancellotite on the lower part, calcareous in the central part, and then cancellotite again in the upper part. But it's quite interesting because you can see also that the thickness of the layer is changing. It's thinner in the lower part, is thicker in the central part, and becomes thinner again in the top. So it's not that simple that it's changing for coarser and therefore finer. There is some internal variability producing that we call layering or banding, and this variation in the thickness of the beds. So all are criteria to identify contours and declarational sequences on the field or using cores in a well. So many evidence of reworking, interruption of segmentation, that is the key to have these, let's say, sandier deposits. And you see the microphases of this calcareous, in this case is more carbonate, and it's mainly contained up to 98% of forames, especially in that we call the non-compacted layer, that's the more endurance layer here in the sample. In Caravaca, Murcia is even better because we can see a complete sequence of deposits in a drift. And normally the long-term variation of grain size is coarsening hour. So it's finer sediment in the base. You remember it was more tabular in seismic, but when you go in the growing phase and at the end of the drift, you have coarser sediment. So that means that the lower part of the sequence, you can see fine grain vibrational sequences and contours. When you go in the middle part, you started to see more coarser contours with these vibrational sequences, not very different to the sample I showed you from Cyprus in the middle part. But when you go to the upper part of the sequence, you started to see something different. And here you can see proper sandy contours and a lot of reworked turbidites. So this is very common, and it's interesting because at the end of the day, when you are working with seismic, you are in the field, that you can learn from this long-term variation is that the current is weaker at the beginning and enhancing all the time up to the top of the drift, and then stopping. And that is why you have a lot of reworking at the top of the sequences. And most of the time, they are initially, usually, turbidites or master deposits being completely reworked or partially reworked by the bottom currents. In this example, for example, on the top, you can see a scour at the base of the turbidity layer, and then the internal deposit on the base deviated completely to the turbidity. What does mean? That initially, the deposits were there because the turbidity flow, and then, as I said, reworked. And this is a nice example of what I try to say here for the Norwegian margin, where you can see these gullies or canyon, and at the end of them, you can see a submarine fan, but all the submarine fans are deviated by the action of the bottom current. In a more extreme situation, like this example from Bernelle, from Brazil, you can see the gullies on the slope, and then you can even not identify the fan because have been fully completely reworked by the action of the erosion current. And the reason you can see now is the sandy deposit developing these sandy ribbons along the margin, parallel to the margin. So finally, implication and future consideration. I am very close to the end now. Implication, you heard many in the previous talk. I'm going to simplify now this for you. So many investing analysis. Why? Because as I said, the features are very, very large. They are in basin scale, sometimes even at the same time in different basins. Another implication is the concept of water masses, because the water masses have been controlled and they are controlling the concept of the accommodation space in the water. And that is why you can see in many areas very large lateral migration of the deposits. As this example from Argentina, from Adam Kirby. Another implication are, as you heard before in paleo methodology, but there is something interesting that you should know based on this recent paper from Charu-Yin, is that on Contourites, especially on the drift, where the current is weaker, as I said, you can preserve higher percentage of organic matter, more than in other deepwater systems, as mid-pelagic sediment or as turbidines. And that is opening a very interesting aspect for future. Other implication, as you heard, geohazard, environmental integrity, ocean policy, energy design, and mineral resources. Normally, in this talk, one of the key questions is, has anybody drilled a contour system, or has anybody found any, reservoir or a field on this system? And the situation is that there are many samples from turbidines, and many, and more every year in mixed system. And the potential for the contourite is there. And some of the mixed system, or that people consider mixed system, could be considered as contouritic as well. So the answer is yes, as far as you have, good reservoir, accumulation of sands, as we saw from the previous speaker, from Chris, and you have a good field, and you have, the condition to develop the field. Future consideration. Well, here you have this fantastic 3D block from Andreas Lake, from the Gulf of Mexico. And you can see mainly two surfaces. One is around 1 kilometer deep, another one is in the present day surface. And analyzing this older surface, you can see the main feature in the seafloor by that time were gravitational, submarine canyons, submarine fans, after deposits. So we can really decode from these morphologies and from the distribution of the feature that for that particular time, the margin was mainly gravity driven. But you compare with the feature today in the seafloor, is really the opposite, because most of the features are parallel to the margin. You can see furrow, channel, etc., that they are all trending parallel. So this is to remember, Sarah said, when the processes are not related. Sometimes this interaction of these processes are desynchronized, like here in the Gulf of Mexico in this example, but other they are synchronized. And I think now, today, there is a growing recognition that processes interact and the whole in the deep sea having that section. So that means that the common is the interaction of processes most of the time. That is why the complexity of the sedimentary facets. A future consideration, I will highlight several. Contourites and also mid-depositional system are critical deep ocean features. They are basin scale. They are under-recognized, but they are omnipresent. And there is a simple reason because the ocean today and in the past always have been in movement, always have been affected by processes. And we have to be in the situation to decode and identify these processes. This feature have an expanded sedimentary record, and this is useful for some reserve line. Very high stratigraphic significance. We started to know that through time, this contract system and the system are especially in a specific time interval. And something that for me, this is the last, very important, the tectonic aspect of this. There is a close link between the onset, the growing, and the end of this depositional system with tectonic, and also with the evolution of the gateways. So here you can see this example for the Cretaceous. In the light blue, you have the opening of the gateways, and in the light orange, you have the closing of gateways. And the opening and the closure of gateways have been the key to have changes in the structuration of the water masses in the past or through time. What does that mean? That means that every time a gateway was open and two oceans started to be connected, you have probably a new water mass affecting to a new part of the continental margin, and therefore you started to have contouritic feature there. And in some point, this feature stopped because there is some tectonic changes and also changes in the gateways. So in a recent publication that is going to be online in 3 weeks, we have compiled since the Jurassic to the Quaternary the evolution of these gateways. And it's quite interesting. I'm going to go just to the general aspect of this compilation. And the general aspect is that in the upper Jurassic to the upper Cretaceous, the circulation was mainly latitudinal, because the main gateways were more trending east-west. Not only, it's a simplification, but mainly. And then there is another period with many changes because plate tectonic in the gateway that is mainly from the Middle Eocene to the Quaternary, where the gateways mainly were trending north-south. And then it's more a latitudinal, longitudinal, I think I said wrongly, longitudinal at the beginning and then now latitudinal connections. And this is very important, not just because, as I said, the onset of new water masses or changes in the stratification. This is very important because that affected or was one of the factors controlling the global climatic condition in our planet. Here you can see that the first period is mainly affecting the warming condition in the Cretaceous. And in the second one, you can see that is mainly controlling the colder condition in our planet. And another implication is in some of the hypotheses for the South-to-Sea theory that is not considering the influence of water masses and oceanographic processes in this model. So, as I said, most of these deposits are along the slope and continental rise, and in those drifts, in those contouritic systems, there is the store of a lot of sediment that they are not getting the deeper. So that is why contourites and mid-depositional systems are a new paradigm for the water sedimentary environment, because from my view, the better knowledge of this system are changing our model, are changing our mind. And for me, the key message from this talk is that we need a shifting mindset to fully understand the influence of these water masses, oceanographic processes in the water setting. And we have to include the drift in future models. And for that, it's not just academia, we need the collaboration from academia and industry. Our group is having a consortium with 11 companies, and it's going pretty well. We are all going the flow, and you want to go also with the flow, please join us. We are looking for industrial partners. And that's it. Just to remember, as you saw before, that we are co-organizing the BOMA sequence in Morocco. So please stay tuned because more information will be soon. And that's all. Thank you very much for your attention.